Hey guys, Buildzoid here, and today we're going to be taking a look at a very special GTX 1080 Ti PCB. This is EVGA's Kingpin edition, named after the extreme overclocker Kingpin, who works at EVGA, and whoa does it show that this card was designed with full intentions of running on liquid nitrogen and smashing world records, especially 3D Mark. We'll go into why, this card is so very LN, extreme overclocking centric. We'll start with the usual, the VRMs.
Before getting to that, this video is brought to you by iFixit.com and the PC Essentials Toolkit, which can be had for $20, making it one of their cheapest yet most complete toolkits. Use code GamersNexus for $5 off to bring that to $15. You can go to iFixit.com/GamersNexus or click the link below for more information.
Starting with the largest, the VCore VRM, located right over here. So that's VCore. That supplies the power used by the GPU core, and it is the most important VRM when overclocking on liquid nitrogen and other subambient cooling methods. So that's one. Behind that, we find the memory VRM. And the memory VRM powers all of the GDDR5X chips around the GPU core. And those are basically the two largest VRMs on the card. All the other ones from here on are minor ones that you don't really have to care about that much. Starting off with this one down here, this is one way to describe this is the VRM that powers the VRMs. So this is known as the variable gate drive. Basically, its job is to convert 12 volts into a voltage between 5 and 10 volts, though it theoretically could go lower, but you wouldn't do that because this VRM produces produces the voltage that the VCore VRM and the memory VRM use to switch their MOSFETs on and off. Then this over here is another one of the minor VRMs. This is the 1 volt PLL PEX voltage. This voltage is, you don't actually need to run this one on liquid nitrogen. It is, however, very, very helpful, but you can get away without it. Of course, this card right here has voltage control available for that. We'll go into more detail later in the video about that. And then up here, we finally find the 1.8 volts VPP for the GDDR5X. So this is a supporting voltage for the GDDR5X memory. Basically, this voltage used to be internal to previous memory systems, except it became external on GDDR5X, as having it external improves efficiency. So, yeah. And this voltage doesn't actually do anything for overclocking, so you don't have to worry about it. So one thing before we get into the details of the PCB here, this is a engineering sample PCB. First of all, you can tell because it's a revision 0.0. The other thing is there's lovely things like this hand soldering right here and this right here, as well as all of the debug headers right over here. So basically, there might be some very minor changes from this PCB to what you end up seeing retail, but the VRMs and the feature set will not be changing. So let's start off with the largest one, the VCore VRM. It is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 phase based on the inductor count, which if you've watched past videos of mine on, looking at PCBs, you would know that you can't actually buy a 10-phase voltage controller, so this card is running a doubling scheme, and it's doubling up 5 phases from the voltage controller right here, and those are doubled up through International Rectifier IR3599s, which you have one here, one here, one here, another one there, and another one there, so that's 5 of them in total, and IR3599s are doublers and or quadruplers. They can do either of those two functions. As a trade-off, these are one of the more basic doubler types. They're not, they don't have some of the advanced features you can get on some other doublers out there, which do actual current balancing between the two phases that they're hooked up to. So as far as the actual voltage controller right over here is concerned, which that is a IR3595, as far as that is concerned, This VRM is a 5-phase. It cannot individually, there's no individual regulation for the actual separate, 10 phases that the VRM ends up with. However, the phases are interleaved, so you do get some of the benefits of a 10 phase, just not all of them. That's sort of the thing. For example, you do get the increased power throughput, the better thermals. You get slightly better voltage regulation because there's less current going through each phase, and since it's interleaved, even if it's badly, not super accurately interleaved, you still get interleaving of the phases, and that leads to basically the VRM putting less strain on the power supply, as well as a side effect, you get better voltage regulation. So, it's better than any 5-phase. It should be better than a 6. And then if it's better than a 7-phase or an 8-phase, that really depends on the details of the implementation. So the RR3595 is a 6+2 phase voltage controller. EVGA is not using the +2 part at all, and the 6 is downgraded to the 5, which then gets multiplied by 2 by the IR3599, and then that, gets you your 10 phases. So that's how the VRM is controlled. I've already said, what the doubling scheme that EVGA is running here does. The 3595 has a switching frequency range of 200 kilohertz all the way to 2 megahertz. However, the 3599 over here only goes up to 800 kilohertz output. And the stock switching frequency on this VRM is 400 kilohertz. So it is clocked a bit. It is a higher switching frequency than many of the other cards. As typically you'll see cards shipping with sort of 300 kilohertz switching frequency. However, to be absolutely certain, I would have to have cards in hand to check what their actual switching frequency is with like a oscilloscope, or because most of the existing 1080 Ti's use analog voltage controllers based on how those are wired, because the frequency is set by a circuit. So you can basically check that circuit to figure out the switching frequency. Yeah, that's the control scheme. In terms of power quality, especially considering that, the capacitor selection and capacitor positioning and that kind of thing also plays a very large role in getting a good stable voltage level. It's really hard to say how this VRM would compare to other VRMs, also with the 1080 Ti not being exactly a huge power-hungry monstrosity like, say, the 980 Ti and other previous architectures where on liquid nitrogen you could easily see a single GPU pulling as much as 1,000 watts under load. So I don't see a problem with running a 10-phase. Yes, higher phase counts could possibly deliver better voltage stability. However, on a 1080 Ti, I don't really think it would actually have any meaningful impact on overclocking, even on liquid nitrogen. So, yeah, that's sort of so I don't really have a problem with the control scheme that EVGA has gone for here. Obviously, it could have more phases. That could also be a waste of PC board space at this point. Now, for the actual power throughput, we're looking at international rectifier power stages, and these are IR3575s. These things are pretty much the best power stage international rectifier makes. These are 60 amps rated, 11 watts of heat output at that current level, and a operating temperature of 125 degrees to achieve this rating. So this VRM right here has a theoretical maximum current throughput of 600 amps with a heat output of 110 watts. And that would be like an overload scenario. So this would blow up the VRM pretty much instantly. But you're not going to hit that. So the VRM is plenty powerful for feeding a 1080 Ti. And under normal operating conditions, this VRM will actually be in its sort of just past the peak of its efficiency curve, as at 220 amps power draw, this VRM will be just around 21 watts of heat dissipation, and that includes driver IC losses, because these are power stages, so all losses are calculated, like in that power loss value is complete, whereas for other VRMs, I usually just look at how much power is lost on the MOSFETs themselves, not on the actual driving circuitry of the VRM as well, which won't be a huge amount, but, you know, it also pulls power, and you can't really ignore it, especially considering how most 1080 Ti's have pretty good VRMs to start with, so the differences aren't, you know, tens of watts. It's a couple watts here, a couple watts there, but this is by far one of the most efficient 1080 Ti VRMs I remember looking at anyway. So, yeah. The other cool feature of the 3575, ignoring its ridiculous power draw and power capability and efficiency, is the fact that it has this metal heatsink piece on the outer casing. So basically, this is a bit of metal that goes straight to the actual silicon inside the MOSFET, and this really improves with keeping internal temperatures on these down, which improves lifespan and reliability. So, yeah, there's a reason why these are international rectifiers best, and since these are power IR power stages from international rectifier, these also feature body braking mode as well as diode emulation mode, which are both, well, body braking mode is a really cool feature for load release voltage stability. So basically, when the card goes from very high load to very low load, body braking mode can be used to really mitigate any kind of big spikes in voltage very, very well. And the 3595 here supports that. The 3575 support that. The 3599 also supports the body braking mode as well. So basically, the VRM can use it. And the other thing is diode emulation mode is basically just a super high power, like it's for super low power usage. The VRM will basically stop using power to turn on the low side MOSFET if you ever pull that little current through it, which won't actually happen because the VRM here, instead of having multiple phases turned on at the same time, the 3595 can switch phases on and off dynamically. So if you're at idle, it won't actually need to run the entire VRM. So it probably won't ever enter body braking mode because as long like the voltage controller can pretty much keep the VRM at peak efficiency under any kind of load condition. So that's, you know, yeah, it's a very nice VCore VRM, as you would expect of a card with the Kingpin name on it. So yeah, moving on to the memory VRM. This thing is ridiculous overkill for memory, but it is nice to see. So, and it also has some weird things. So the memory VRM right here is a 1, 2, 3 phase design. It is controlled by this voltage controller, because if you remember, this was a +2 and we're not even using that. And this voltage controller right here is an IR3570. And this goes, again, 200 kilohertz to 2 megahertz. But this is a 3+2 phase voltage controller. And EVGA is not using the +2 part. They're using the 3 part because they want 3-phase memory power. This can actually, like, 3-phase memory power is really overkill, but it can actually help with overclocking range on memory, so I don't think it's needless. What is kind of needless is that EVGA has opted to yet again use IR3575s. End result is this memory VRM has a theoretical maximum current throughput of 180 amps, assuming you have, you know, ridiculous cooling capabilities. The side effect of that, however, is that the memory VRM under normal load conditions, and even overclocked, you won't really see the memory VRM really ever exceed 30 amps of current throughput. This thing will only ever put out about 2 to 3 watts of heat. So this thing will run ice cold. The memory VRM on this card will run absolutely ice cold, even without the heatsink. And, you know, EVGA with their new ICX coolers are just going absolutely insane with heatsinks. So the memory VRM has a, you know, it is heat-synced anyway, even though I honestly wouldn't bother because these are overkill. Really, really overkill for the application you see here. There's you know, there's 1080 Ti's out there with single-phase memory VRMs with no active cooling on the memory VRM at all. So, yeah, really, really overkill. The 3 phases improve, you know, voltage regulation on the memory as well. So, yeah, it's a really nice memory VRM. Interesting little thing to note is that the memory VRM's main capacitor bank is actually located all the way over here, which is just kind of cool and worth pointing out because it is kind of interesting, because this right here is the ground plane, and then you can see that you have the memory power plane sort of going around all the memory chips like that. So yeah, these capacitors right here are for the memory VRM. And it makes sense that they're located over here because generally with decoupling capacitors and filtering capacitors, you want to put them as close to your load as possible. And the load for the memory VRM is, of course, the memory chips themselves. So putting them right here makes sense. A lot of other manufacturers, to basically get the capacitors close enough to the memory chips, what they'll do is they'll like cram the memory VRM up here or in this area, or they'll mess up, like they'll split some of the phases off of the VCore VRM, shift it down into this area so that the VCore VRM is sort of longer in its layout. But EVGA opted for a kind of interesting layout with having the capacitors really far away from the actual chokes of the VCore memory VRM right here. So yeah, now let's move on to the minor VRMs. The cool thing about all of the minor VRMs, the VPP, the PLL, and the variable gate drive VRM, all three of these are using a fully integrated buck converter, which is an IR 3899. This thing has a maximum current throughput of 9 amps and 9 amps 10 volts. Yeah, 9 amps 10 volts output. It's going to produce about 2.4 watts to 3 watts of heat. So basically this thing is plenty powerful. Nothing to worry about in terms of, you know, powering the PLL or the VPP or the, you know, actual VRM itself. So the VRM selection that EVGA has gone for here is excellent, which, you know, you wouldn't expect anything less of a Kingpin branded card. So now let's get on to the actual sort of cool LN2 overclocking features, because it's one thing to make a GPU that doesn't blow up. Well, one thing to make a card, a PCB, that doesn't catch on fire when you put it under liquid nitrogen, as in you make the VRM strong enough to not get destroyed when you really, really push the card. The thing about that is that's relatively easy. Basically, anyone can make a really large, massive VRM, strap a big heatsink on it, and get a good current rating. Now, admittedly, the better manufacturers will actually do that while maintaining good efficiency levels and that kind of thing, but generally anybody can achieve that. The harder part is making a card that isn't a massive pain to work with, and that's a lot of what EVGA sort of like. That's what makes the Kingpin cards really special for extreme overclockers, because the Kingpin cards are one of the few lines of cards, if not the only line of cards, where you can buy one of these, and assuming you have faith that the card wasn't dead on arrival, you can buy, insulate, and run on LN2 without doing anything else to the card, because you have software and hardware support for everything you could need. And that is achieved by the basically voltage controller selection, as well as all of the extra headers you have around this area of the card. So the 3595, the 3570, these are both fully digital international rectifier voltage controllers, so they can be controlled through software, and both of them are controllable through this USB header. That USB header gives you voltage control, LLC settings. Yeah, I can't write that fast. Also, you get temperature monitoring for the many sensors scattered around the card. And you also get, well, for the voltage controls, you get obviously both VCore and memory. You also get the 1 volt PLL, which I did say earlier is kind of optional for LN2. Like, you can totally get away with running a card with just VCore control. I've done that. I have a 1070 that I ran on LN2 that, you know, I only had voltage control for VCore because I could not be bothered doing all the other mods around the card. So, like, I would need to physically modify, because basically, if you buy most other cards, you end up having to modify a ton of things, and that just takes forever. It's risky. It's a pain. Sometimes you can't find data sheets. You know, it really makes everything a lot harder for extreme overclocking. Like, you have even very basic things, like, for example, clearance, component clearance. For example, this card right here, there's no tall components anywhere in this area, which, you know, you might think, oh, it's not really that special. Well, it actually is. Because if I try to mount most LN2 pots have only a few millimeters of clearance in this entire area right here. So you basically have a rectangle where nothing taller than a couple millimeters can be, or the LN2 pot won't fit on the card. Well, it just so happens that a lot of manufacturers like to put memory VRMs right over here, and those memory VRMs end up with capacitors sorta in this area. So if you're an extreme overclocker, you basically end up in a situation where you either have to move components already on the card around, remove them, and figure out someplace else to mount them, because you need to have them, you know. Usually it's capacitors and like chokes. So you'll have to like desolder a choke and resolder it on the back of the card, and you better pray that your card is through hole at that point, because some, you know, these are surface mount chokes. You can't actually move them. They have to be on the side of the card where they were intended to be mounted. So in situations where you can't move the components elsewhere onto the card, you're stuck running something known as a base extension for an LN2 pot, which is essentially just a chunk of copper that sits between the LN2 pot and the GPU core to give you extra height, extra clearance from the PCB for the LN2 pot. And those ruin your thermal performance, like absolutely ruin it, because that extra block of copper includes an extra layer of thermal paste to connect it to the base of the pot. Then there's a thermal paste connecting the extension to the GPU core. So 2 extra layers of thermal paste. Thermal paste at very low negative temperatures doesn't really, like, the less of it there is, the better. The less layers of thermal paste, the better. Like, it's a massive thermal insulator at very low temperatures. Even the high-end thermal pastes are. The centimeter or so of copper is a massive thermal barrier. It is so bad, in fact, that if you go from, like, say, for example, my GTX 1070, at idle, I can have the card as cold as minus 170 degrees centigrade. Once the card goes under load, it very quickly climbs back up to minus 120 degrees. And that's entirely because of that block of copper just sitting in there, acting like a thermal insulator between the GPU core and the LN2 pot. So, you know, that's like a really basic design thing for a manufacturer to take care of. You just don't put components that are that tall in this area of the card. But a lot of cards don't actually do that, and then if you're an extreme overclocker, they're just not an option for you. This, being a Kingpin card designed to run on LN2, only has this and this, which are like the only potential clearance concerns, and those are both very low profile chokes. So pretty much any LN2 pot is going to fit on this card, which is really, really nice if you're an extreme overclocker. So yeah, so you get the voltage controls, the LLC, the temperature monitoring, and then up here you get more voltage control, this time through the EVBot header. This is a USB. That's a USB header down there. This is the EVBot header. And the thing about the EVBot is it's basically a dongle that EVGA used to make for their cards, which you can plug in and get voltage control and LLC settings and that kind of things. So basically it does everything the USB port does, except the EVBot is unavailable. You can't buy it. It hasn't been available for several years now. So that's kind of unfortunate, but I don't really see that as a problem since the USB header kind of does everything the EVBot header does. But for guys who like using the EVBot, you know, yeah, they can. Next to that, we find these 3 2-channel dip switches, which are actually a permanent feature of the card. These disable various protections like over temperature, over current, any kind of limitations. You can switch them off with physical switches on the card, so no more limits. Next to that, you find some very basic troubleshooting LEDs. So you have a LED indicating 12 volts, 3.3 volts, PLL, memory, GPU. 12 volts, 3.3 volts is basically check your PCIe slot, check your power cables. PLL, memory, and GPU. If one of those is not lighting up, you have a very, very serious problem, because it basically means you're not getting VCore or PLL or GPU power. I mean, core power, memory power, or PLL power. And if one of those is missing, if you're on LN2, there's a good chance some part of the card is really, really wet, and it's not working because of that. If you're not on LN2, the card is probably dead. So, yeah, but it does save some time with troubleshooting, because if you're trying to post and you're not getting any display output for no apparent reason, you know, you can just quickly check if the card is even getting power properly. So these are kind of useful for troubleshooting that. Then up here we find the Probit belt. Basically this is there's a little header that goes into that with a bunch of wires coming out of it. Those are terminated in it's not an alligator clip, but it's basically a terminal that you can plug digital multimeter probes into really, really snug. I have a few motherboards that come with something very, very similar. These are awesome. I love these. And these are extremely useful because when you're running cards on liquid nitrogen, you can't really run monitoring software on the system you're doing your extreme overclocking on. So you can't monitor voltages with software. So you have to rely on digital multimeters. And for most cards, that means you're going to be soldering on your own probe points, because after you've insulated a card, you can't exactly go and stab the legs of a capacitor while the card is running 3D Mark with LN2 needing to be poured. So this is very, very handy, and again, it just saves time from the usual ritual of buy the card, test the card, mod everything on the card, and then finally run it. So yeah, this is a very nice feature. Then we have what looks to be a third SLI connector. It's not a third SLI connector. It's some super secret feature that EVGA currently won't reveal what it actually does. And then next to that, we find a 3-channel BIOS switch. There's a regular BIOS, a backup of the regular BIOS, and an LN2 BIOS. I'm not entirely sure what the LN2 BIOS does, but I imagine it disables any limitations that you would normally run into, like like the actual NVIDIA power limit would be lifted and that kind of thing. So yeah, the card is fully, you know, it is very much one of those cards where you can just buy it, test that it works, insulate it, and run it on LN2. That's really what makes one of these cards so very, very special for extreme overclockers, because most of the time you need to do a ton of modding, and you know, sometimes you just can't even do the mods because, oh look, this component doesn't actually have a data sheet that I can look up on the internet. So for extreme overclockers, this card is an absolute treat. For gamers and, you know, normal people, I feel like the ridiculous just design and engineering that went into this card is really, really wasted. But yeah, you know, if you want like a Formula One that you're gonna drive daily, this is the card for you. This is pretty much a Formula One because this thing, it was built to break, you know, overclocking records first, and then everything else was like, well, it can technically play games. So yeah, I don't really have any complaints, except maybe smarter doublers or more phases, maybe, like, if not, you know, if they don't want to do a 12 or a 14 or a 16 phase, why not just do an 8 phase? That could have been another option. But I totally understand why putting a 14 phase or a 16 phase on a 1080 Ti is just a complete waste of space, because a 1080 Ti will never pull that much power, even on liquid nitrogen. So, yeah, this is a very, very impressive card. And it's a Kingpin edition. It completely lives up to the name that to the legacy that the previous Kingpin edition cards have established. So that's it for this video. Thank you for watching. Like, share, subscribe, leave a comment down below. And if you would like to support what we do here at Gamers Nexus, then you can donate to our Patreon down in the description below. And if you would like to see more videos like this, as well as other extreme overclocking stuff, then you could head over to my channel called Actually Hardcore Overclocking. Thank you, and goodbye.